October 23, 1943. In a dimly lit industrial laboratory on the outskirts of Tokyo, Chief Metallurgist Takeshi Nakamura peered through his microscope at a small section of metal harvested from an American Sherman tank transmission. Outside, autumn rain pattered against the windows, masking the distant sounds of air raid sirens during yet another drill. Nakamura and his team of 4 engineers were certain they would find evidence of American technological inferiority, proof that would validate their own superior manufacturing processes and restore confidence in their increasingly troubled war machine. Before we dive into this story, drop a quick hi in the comments and tell me where you're watching from. It really helps support the channel. What Nakamura and his team would discover in the coming months would not only challenge everything they believed about American industrial capabilities, but would fundamentally transform their understanding of how a nation's cultural values and manufacturing philosophy could be encoded into something as seemingly mundane as a tank transmission. The captured Sherman had arrived at the Imperial Japanese Navy Technical Research Institute in Tokyo Bay 3 weeks earlier. It had been recovered mostly intact from the island of Guadalcanal following the withdrawal of Japanese forces, a rare prize in a conflict that was producing increasingly bad news for the Empire of Japan. Lieutenant Commander Hideo Watanabe, who oversaw the analysis program, had personally selected Nakamura to lead the metallurgical investigation. "You understand what is at stake here," Watanabe had said during their initial meeting, his voice low and steady. "We need to know why these American tanks keep running when ours break down. Our Type 97 medium tanks require maintenance after 100 kilometers, yet reports from the field suggest these Shermans operate for 500 or more without major service." Nakamura had nodded, feeling the weight of responsibility. At 42 years old, with 20 years of experience in metal composition and manufacturing processes, he was considered among the finest metallurgists in the empire. Before the war, he had studied for 3 years at the Massachusetts Institute of Technology, returning to Japan in 1938 as tensions between the nations escalated. "I will not fail, Commander," Nakamura had replied, bowing deeply. Now, as he adjusted the microscope's focus, Nakamura called over to his assistant, Kenji Tanaka, a young engineer just 2 years out of the Imperial University. "Tanaka, what was the hardness rating on Section 4 again?" he asked, not looking up from the eyepiece. Tanaka consulted his meticulously kept notebook. "Rockwell C-scale indicates 47.3, sir, consistent with the 3 previous samples." Nakamura frowned. This matched the specifications their intelligence had suggested for American armor plate. But the consistency was surprising. Japanese manufacturing typically showed variations of at least 2 points between samples, yet all 4 specimens from different parts of the transmission showed nearly identical hardness values. The laboratory door slid open, and in walked Watanabe, accompanied by Dr. Ichiro Yamamoto, the Naval Arsenal's chief production engineer. Nakamura straightened immediately, as did the other members of his team. "Commander, Doctor," Nakamura said with a bow, "we were just discussing our initial findings." Yamamoto moved directly to the disassembled transmission components laid out on the central table. His eyes narrowed as he picked up a gear, turning it over in his hands. "These appear quite ordinary," Yamamoto observed. "Nothing that would suggest exceptional performance capabilities." Nakamura approached the table. "That is precisely what puzzles us, Doctor. The materials and design are not revolutionary, yet field reports indicate these transmissions operate under conditions that would cause our equivalent units to fail within hours." Watanabe crossed his arms. "Could it be exaggeration? American propaganda to demoralize our forces?" "I considered that possibility," Nakamura replied, "but we have documented evidence from our own observers. During the Philippine campaign, captured Shermans were operated by our forces for 3 weeks without maintenance before being abandoned due to fuel shortages, not mechanical failure." The room fell silent as the implications sank in. Japan was already struggling with critical material shortages. The naval blockade was tightening each month, and the nation's industrial base was straining under constant air attacks. If American equipment truly possessed significant reliability advantages, the gap between the warring powers would only widen. "Continue your analysis," Watanabe finally said. I want a comprehensive report in 30 days. Focus on whether we can implement any discoveries into our current production methods without retooling entire factories. After Watanabe and Yamamoto departed, Nakamura gathered his team. Besides Tanaka, there was Hiroshi Sato, a metallurgical chemist specializing in steel alloys, Akio Ishikawa, an engineer with expertise in mechanical stress analysis, and Fumiko Hayashi, the only woman on the team, who had studied industrial manufacturing processes in Germany before the war. "We need to be more methodical," Nakamura told them. "Tanaka, continue with the metallurgical composition tests. Sato, I want a complete analysis of the heat treatment signatures. Ishikawa, focus on wear patterns and stress points. Hayashi, examine the manufacturing marks for clues about their production methods." As the team dispersed to their tasks, Nakamura returned to his microscope. Something about the grain structure of the metal nagged at him. It appeared almost too consistent, too uniform. In Japanese manufacturing, such precision was achieved only in the most critical aircraft components, certainly not in tank transmissions that would likely be damaged or destroyed in combat. Over the next week, the team worked long hours, often sleeping on cots in the laboratory as air raid sirens became more frequent. Their initial findings only deepened the mystery. The alloy composition is standard, nothing exotic. Sato reported during their morning briefing 7 days into the project. Chromium, nickel, and molybdenum percentages are within the ranges we use for our own heavy equipment. The gear teeth show minimal wear despite evidence of extensive use, Ishikawa added. Based on the stress patterns, I estimate this unit operated for at least 700 kilometers before capture. Hayashi spoke last, her voice betraying a hint of excitement that was unusual for her typically reserved demeanor. The machining marks are revealing. Each component shows evidence of being produced on automated machine tools with extremely tight tolerances. More importantly, I found this. She handed Nakamura a gear shaft, pointing to a barely visible marking. These are inspector stamps. I counted 17 different marks on various components. 17 inspections for one transmission? Nakamura asked, surprised. Not just inspections, Hayashi corrected. 17 different inspectors. I compared the marking styles. These components passed through many hands during production. That evening, after the others had retired, Nakamura sat alone at his desk, reviewing their findings. The Sherman tank transmission contained no technological breakthroughs, no exotic materials, no revolutionary design concepts, yet it performed far beyond what Japanese engineers could achieve with similar resources. His mind drifted back to his time in America. He had toured automobile factories in Detroit, watching with fascination as vehicles moved along assembly lines, each worker performing a specific task before the chassis moved to the next station. At the time, he had been impressed by the efficiency, but found the process soulless compared to the craftsman approach still prevalent in much of Japanese industry. Now he wondered, could that American system of mass production actually create superior results? The notion challenged everything he had been taught about quality manufacturing. As November arrived, bringing colder temperatures and increased fuel rationing, the team delved deeper into the Sherman's transmission secrets. Nakamura authorized destructive testing of several components, allowing them to analyze the internal composition and heat treatment more thoroughly. The heat treatment is applied with remarkable consistency, Sato reported, after examining cross-sections of 3 identical gear wheels. The case hardening depth varies by less than 0.1 millimeters across all samples. Nakamura nodded thoughtfully. In our production, such consistency would require master craftsmen overseeing each heat treatment bath. The Americans must have found a way to standardize this process for mass production. That's not all, Tanaka interjected. Look at these microfissure patterns. He pointed to microscope photographs spread on the table. Every gear shows similar microscopic stress cracks, but they never propagate beyond 0.3 millimeters. It's as if they're designed to crack in specific ways. This observation triggered a memory for Nakamura. During his studies at MIT, a professor had discussed the concept of designed failure modes, the idea that components could be engineered to fail in predictable, non-catastrophic ways. Rather than striving for perfection in each part, American engineers accepted minor imperfections, but ensured they wouldn't lead to system-wide failures. The contrast with Japanese philosophy was striking. Imperial engineers sought flawlessness in each component, a reflection of the Bushido spirit applied to industrial production. Perfection was the goal, and anything less was considered dishonorable. Yet this pursuit of perfection required skilled craftsmen, limited production capacity, and left little room for the realities of battlefield conditions. 2 weeks into their investigation, an unexpected visitor arrived at the laboratory. Colonel Masanobu Tsuji, a military intelligence officer known for his harsh tactics and fanatical devotion to the emperor, swept in flanked by 2 junior officers. "I understand you are analyzing American equipment," Tsuji said without preamble. "I require your findings immediately for a report to Imperial General Headquarters." Nakamura bowed respectfully, but felt immediate concern. Tsuji's reputation for twisting information to suit his narrative was well known. "Colonel, our analysis is still ongoing. We have preliminary findings, but nothing conclusive to report yet." Tsuji's eyes narrowed. "Are you suggesting that after 2 weeks, your team has discovered nothing of value? Perhaps we have misplaced our faith in your abilities." The threat hung in the air. Nakamura chose his next words carefully. "We have made several significant discoveries, Colonel. The American transmission shows evidence of mass production techniques that sacrifice ultimate performance for reliability and ease of manufacture. Their approach emphasizes standardization over optimization." "So you confirm their technology is inferior," Tsuji said with satisfaction. "Not inferior, Colonel. Different in philosophy," Nakamura corrected gently. "Their transmission will never perform with the peak efficiency of our best designs, but it will continue functioning under conditions that would cause ours to fail." Tsuji's expression darkened. "You speak dangerously close to admiration of our enemy, Professor Nakamura. Need I remind you of your duty to the Emperor?" Before Nakamura could respond, Lieutenant Commander Watanabe entered the laboratory. Seeing the confrontation, he quickly intervened. "Colonel Tsuji, this technical analysis falls under naval authority as specified by Imperial Directive 1942-7, Watanabe stated firmly. "Professor Nakamura reports directly to me, and I have not authorized the sharing of findings beyond my command structure." For a moment, tension crackled between the 2 officers. Though Watanabe outranked Tsuji, the colonel's political connections made him dangerous. Finally, Tsuji gave a curt bow. "Very well, Commander, but I will inform my superiors of this obstruction. Japan cannot afford interdepartmental rivalries when our national survival is at stake." After Tsuji departed, Watanabe turned to Nakamura. "You must be more careful, Professor. Men like Tsuji see admission of American strengths as treasonous. What have you actually discovered?" Nakamura led Watanabe to his office, closing the door before speaking. "Commander, what we're finding challenges fundamental assumptions about industrial production. The Americans have created a manufacturing system that produces consistent quality across millions of components without requiring master craftsmen." He spread photographs on his desk. "These are microscopic images of gear teeth from the Sherman transmission and our Type 97. Notice the consistency in the American sample versus the variability in ours. Their mass production creates reliability through standardization, while our handcrafted approach creates both excellence and flaws." Watanabe studied the images silently before asking, "Can we replicate their methods?" "Not without completely restructuring our industrial philosophy," Nakamura admitted. "We would need to retrain our workforce, redesign our factories, and standardize our production methods. Even if we started immediately, it would take years." "Years we do not have," Watanabe murmured. 3 days later, the laboratory received unexpected news. An intact Sherman tank had been captured in the Philippines and was being shipped to Japan for comprehensive analysis. Nakamura's team would be expanded and given access to the complete vehicle. "This is an unprecedented opportunity," Nakamura told his team. "We will be able to examine how the transmission functions within the entire drive system." The captured Sherman arrived in early December at Yokosuka Naval Base. Despite suffering minor damage during combat, the tank was operational. Nakamura and his team were assigned a dedicated warehouse for their expanded research. The Sherman M4A2 medium tank stood imposingly in the center of the space, its olive-drab paint scarred, but its mechanical components largely intact. A group of naval engineers had already begun documenting the vehicle's dimensions and performance specifications. What immediately struck Nakamura was the apparent crudeness of some elements contrasted with the refined functionality of others. The cast hull showed visible manufacturing marks that Japanese engineers would have polished away. The engine compartment contained accessible components, arranged for easy maintenance rather than optimal space utilization. Yet when they started the radial engine, it roared to life instantly despite weeks of neglect. "This should not be possible," muttered Ishikawa as the tank's engine settled into a smooth idle. "Our tanks require extensive maintenance after sitting unused for even a few days." Nakamura walked slowly around the Sherman, taking in details that spoke to its design philosophy. The track links could be replaced individually without disassembling the entire track. Access panels opened with simple latches rather than precision-fitted bolts. Everything about the design emphasized field repair and reliability over technical sophistication. For 2 weeks, the team methodically documented every aspect of the Sherman's powertrain, from engine to final drive. They disassembled components, tested materials, and even operated the tank on a specially constructed test course to measure performance under various conditions. What emerged was a picture that fundamentally challenged Japanese military engineering doctrine. The Sherman was designed by engineers who anticipated it would be operated by farm boys with minimal mechanical training, maintained in field conditions with basic tools, and expected to function despite neglect and damage. It represented a democratization of technology that was alien to the Japanese military mindset, which assumed highly trained crews and technical specialists. During this period, Nakamura began keeping a private journal of his more philosophical observations, writing late at night in the small apartment he maintained in Tokyo, though he spent most nights at the laboratory. "The American approach represents a profound difference in how they view the relationship between humans and machines," he wrote on December 14th. "In our philosophy, the operator must elevate himself to the level of the machine's sophistication. The American philosophy brings the machine down to the level of the common operator. We create tanks that require experts to maintain. They create tanks that can be maintained by anyone. This is not merely a technical distinction, but a cultural one." On December 18th, Nakamura was summoned to a high-level briefing at Naval Headquarters. Present were Vice Admiral Jisaburo Ozawa, several senior naval engineers, and representatives from the Army Technical Bureau. Nakamura noted with concern that Colonel Tsuji was among them. Admiral Ozawa began without preamble. "Professor Nakamura, I have reviewed your preliminary reports on the American Sherman tank. Your findings are disturbing. You suggest that their mass production methods create advantages we cannot quickly match. Explain yourself." Nakamura stood and bowed deeply before responding. "Admiral, our analysis reveals that American industrial methodology emphasizes standardization, interchangeability, and designed tolerance for imperfection. Their tanks can be produced in vast numbers by workers with minimal training, using automated machinery." He displayed several photographs on a projector. "This gear from the Sherman transmission shows machining marks indicating it was produced in under 5 minutes on an automated lathe. The equivalent component in our Type 97 requires nearly 45 minutes of work by a skilled machinist." "But surely our component is superior," interjected one of the Army engineers. "In isolation, yes," Nakamura acknowledged. "Under perfect conditions, our transmission delivers 2% better power efficiency. But the American transmission will continue functioning after damage that would render ours inoperable, can be repaired by a driver with basic tools, and can be produced at a rate of thousands per month versus hundreds for ours." The room fell silent as the implications became clear. Japan's industrial base, already strained by material shortages and bombing, could not compete with American mass production. For every tank Japan painstakingly crafted, America could produce 10 with greater field reliability. "You paint a grim picture, Professor," Admiral Ozawa finally said. "What do you recommend?" Before Nakamura could respond, Colonel Tsuji interjected, "This analysis overestimates American capabilities and underestimates Japanese spirit. Our craftsmen put their souls into each component they create. The Americans use unskilled laborers producing soulless machines. Spirit will overcome material advantages." Nakamura watched several officers nod in agreement and realized how deeply the military culture was embedded with such thinking. He chose his next words carefully. "The spirit of our workers is unquestionable, Colonel. However, we must recognize that on the modern battlefield, quantity has a quality all its own. I recommend we immediately implement simplified designs for critical components, focusing on reliability over peak performance. We should standardize parts across vehicle types wherever possible and develop maintenance protocols that can be performed by ordinary soldiers." The meeting concluded without clear decisions, but Nakamura left with a growing sense of urgency. The technological and philosophical gap he had discovered went far beyond tank transmissions. It represented fundamentally different approaches to industrialized warfare. As 1943 drew to a close, air raids over Tokyo intensified. Nakamura's team was ordered to relocate their research to a facility near Nagoya, farther from the capital and potential bombing targets. The Sherman tank was transported by rail, accompanied by armed guards to prevent American agents from destroying this valuable intelligence asset. The new facility, partially built into a hillside for protection, offered more space but fewer resources. Fuel for testing became scarce, and the team often worked by lamplight as electricity was rationed. Despite these challenges, they continued their analysis, expanding beyond the transmission to examine the entire vehicle's design philosophy. In early January 1944, they received an unexpected resource: Technical Sergeant Frank Miller, an American tank commander captured in the Philippines. Though initially reluctant, Miller had agreed to provide technical information in exchange for better treatment. Nakamura was surprised when the American was brought to the research facility under guard. Miller was a stocky man in his early 30s, with a farmer's weathered complexion and powerful hands. Despite his prisoner status, he carried himself with quiet dignity. Nakamura addressed him in English. "Sergeant Miller, I am Professor Nakamura. I studied engineering at MIT before the war. We are analyzing your Sherman tank and have questions about its maintenance in field conditions." Miller's eyes widened slightly at Nakamura's fluent English. "You went to MIT. I was studying engineering at Michigan State before I enlisted, never finished." This common ground, however tenuous, established a basis for communication. Over the next 3 days, Miller provided invaluable insights into how Sherman tanks were maintained in combat conditions. "The beauty of that transmission," Miller explained as they stood beside the opened access panel, "is that you don't need to be a genius to fix it. I trained as a mechanic for just 8 weeks before shipping out. Most of my crew had no mechanical experience at all before the Army." "Yet you could maintain this complex vehicle?" Nakamura asked. Miller laughed. "That's just it. It's not that complex. Everything is designed so you can get to it, fix it with basic tools, and get moving again quickly. We had a saying, if you can't fix it with a hammer, a screwdriver, and some wire, it's not worth fixing in the field." This conversation revealed another dimension to American engineering philosophy: the democratization of technology. While Japanese equipment often required specialized knowledge, American designs assumed minimal training and emphasized field expediency over technical optimization. "How much time did you typically spend on maintenance?" Nakamura asked. "Factory recommendation was 10 hours maintenance for every 100 hours operation," Miller replied. "But in combat, we rarely had that luxury. The Sherman can run a long time on minimal care if needed." When Miller was returned to the prisoner camp, Nakamura gathered his team to discuss what they had learned. "We have been approaching this analysis from the wrong direction," he told them. "We've been evaluating the Sherman as a technical achievement, but its true innovation is social and organizational. It represents an entirely different relationship between technology, industry, and human operators." Hayashi, who had been unusually quiet during the Americans' visit, finally spoke. "It reminds me of something I observed in Germany. The German tanks are individually superior to the Sherman in almost every specification, yet their factories cannot produce them quickly enough, and they break down frequently. The Americans seem to have optimized for the entire system, production, operation, maintenance and replacement, rather than for the individual vehicle. This system-level optimization became the focus of Nakamura's final report, completed in February 1944. Titled Analysis of American Industrial Methodology as Demonstrated in the M4 Sherman Tank Transmission, the report went far beyond technical specifications to address fundamental differences in engineering philosophy. Nakamura wrote in his conclusion, "The Sherman tank represents not merely a weapon system, but an industrial and logistical approach that Japan cannot currently match. American engineers have designed for mass production, field maintenance, and operational reliability at the expense of theoretical performance maximums. Their transmission will never achieve the peak efficiency of our best designs, but it will continue functioning under conditions that would cause ours to fail completely." He continued with recommendations. "We must immediately implement standardization across our weapons programs, simplify designs to allow production by less skilled workers, and redesign components for field repairability. Without these changes, the material advantage of our enemy will continue to grow regardless of the spiritual strength of our forces." The report was submitted to Naval Headquarters in mid-February. For several weeks, Nakamura heard nothing, continuing his analysis of other Sherman components while awaiting orders. Then on March 10th, he was summoned to meet with Admiral Ozawa. The Admiral's office showed signs of the increasing pressure Japan faced. Maps on the wall marked with recent territorial losses, stacks of reports detailing resource shortages, and the grim expression on Ozawa's face all spoke to the deteriorating situation. "Professor Nakamura, your report has caused quite a stir," Ozawa began. "Some at Imperial Headquarters consider it defeatist. Others find its technical assessments sound, but its conclusions politically unacceptable." Nakamura remained silent, awaiting the Admiral's personal verdict. "I find it illuminating," Ozawa continued unexpectedly. "You have identified a fundamental mismatch between our industrial philosophy and the requirements of modern warfare. Unfortunately, implementing your recommendations would require resources we no longer possess and time we do not have." The Admiral stood and walked to the window, looking out at Tokyo Bay. "I am authorizing a limited implementation program. Your team will identify critical components from 3 weapon systems that can be immediately simplified for mass production. Focus on items with the greatest impact on field reliability." This was far less than Nakamura had hoped for, but more than he had realistically expected. "Thank you, Admiral. We will begin immediately." "There is something else," Ozawa said, turning back to face him. "Colonel Tsuji and his faction are not pleased with your findings. They have questioned your loyalty, citing your American education. I have protected you thus far, but you should be careful." Nakamura bowed deeply. "I understand, Admiral. My loyalty is to Japan and its future, which requires honest assessment of our challenges." In the months that followed, Nakamura's team worked to redesign critical components for the Type 100 medium tank, focusing on simplification and field repairability. They faced resistance at every turn, from traditionalist engineers who valued craftsmanship over standardization, from military officers who considered simplification dishonorable, and from factory managers struggling with declining resources. Yet they achieved modest successes. A redesigned road wheel reduced manufacturing time by 60% while increasing durability. A simplified track tension system could be adjusted by drivers without specialized tools. A standardized filter system worked across multiple vehicle types, reducing logistics complexity. These small victories could not stem the tide of Japan's deteriorating position. As American forces advanced across the Pacific, resources became increasingly scarce. By late 1944, Nakamura's project was one of many scaled back to divert materials to more immediate needs. In December 1944, the research facility near Nagoya was damaged in an air raid. Though no team members were seriously injured, their equipment and documentation suffered. The Sherman tank, which had provided such valuable insights, was destroyed by a direct hit. As Japan entered the final months of the war, Nakamura continued to advocate for industrial reform, even as the possibility of implementation vanished. His final wartime report, dated June 1945, was never officially filed, but preserved in his personal papers. In it, he wrote, "The lesson of the Sherman tank transmission extends far beyond this conflict. Future industrial competition will be won not by those who create the finest individual products, but by those who master the entire system of design, production, distribution, and maintenance. Japan must learn this lesson if it hopes to rebuild from the destruction that now engulfs us." The surrender in August 1945 found Nakamura in Tokyo, where he had returned after the research program's termination. When American occupation forces began seeking Japanese technical experts to assist with reconstruction, his name appeared on their list due to his MIT background. In October 1945, Nakamura was visited by an American officer, Major Robert Wilson, who had been assigned to evaluate Japanese industrial capabilities for peaceful redevelopment. Professor Nakamura, Wilson greeted him in the temporary office provided by occupation authorities. "I understand you led the analysis of our Sherman tank during the war." Nakamura tensed, uncertain if this constituted a war crime under the new regime. "Yes, Major. It was technical analysis, purely for engineering purposes." Wilson smiled. "Relax, Professor. We're not here about that. In fact, I've read translations of your reports. Impressive work. You understood something about American manufacturing philosophy that many of our own engineers couldn't articulate." This began an unexpected collaboration. Nakamura was appointed as a consultant for Japan's industrial reconstruction, helping to implement the standardized manufacturing methods he had first observed in the Sherman's transmission. In 1952, as the occupation ended and Japan regained sovereignty, Nakamura was invited to Detroit to observe American automotive manufacturing. The assembly lines he toured had evolved from wartime production but maintained the core philosophy: standardization, interchangeability, and designs that accommodated human limitations rather than demanding human perfection. Standing on an observation platform above a factory floor where thousands of automobiles took shape with methodical precision, Nakamura reflected on the journey that had begun with a single transmission. The manufacturing principles he had discovered during wartime analysis were now helping to rebuild Japan's economy, transforming it from a military power to a commercial one. What had been a bitter lesson in defeat had become the foundation for an economic renaissance. The secret of the Sherman's reliability, the willingness to sacrifice theoretical perfection for practical functionality, to design for the realities of mass production rather than the ideals of craftsmanship, had become embedded in Japan's new industrial philosophy. In the decades that followed, as Japanese manufacturers became world leaders in quality and reliability, few remembered that this transformation began with the analysis of an enemy tank transmission. Nakamura, who eventually became a professor at Tokyo University and a key advisor to emerging Japanese automotive companies, never forgot. On the 50th anniversary of the war's end, now an elderly man in his 90s, Nakamura was interviewed by a historical journal about his wartime work. Asked what he considered the most important lesson from his analysis, he smiled thoughtfully. "The Sherman tank taught us that in modern industry, perfection is the enemy of good enough. American engineers understood that a component that can be produced in thousands, repaired by anyone, and functions reliably under adverse conditions will prevail over one that is theoretically superior, but practical only under ideal circumstances." He paused, then added, "But they also showed us something more profound, that how you make something is as important as what you make. The production system itself, the philosophy behind it, determines success more than any individual technical specification. This lesson rebuilt Japan." Today, the influence of those wartime analyses can still be seen in Japanese manufacturing, though transformed through decades of refinement and innovation. The Toyota production system, which revolutionized global manufacturing in the later 20th century, incorporated many principles that Nakamura first observed in that Sherman transmission: standardization, designed-in repairability, and system optimization rather than component perfection. What began as an attempt to understand an enemy's technology became a foundation for peacetime prosperity. The Sherman tank's true legacy was not the battles it won, but the industrial philosophy it embodied. A philosophy that would help transform a defeated Japan into an economic powerhouse. In Nakamura's personal papers, preserved at the Tokyo University archives, his final reflection on the subject provides a fitting epitaph for this story. The greatest technological achievement is not the creation of complexity, but the simplification that makes complexity reliable, accessible, and reproducible. This was the secret encoded in the Sherman's transmission, not how to build the best tank, but how to build tanks best. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.